like this. So how do you do this? Okay? So given this, m of n is 2 times m of n minus 1 plus 1 for n greater than 1, and then m of 1 is 1. So given this, so since this is m of n is 2 times n minus 1 plus 1, we can write m of n minus 1 likewise as what? 2 times m of n minus 2 plus 1. So we replace n with n minus 1. So n is n minus 1. So n minus 1 minus 1 n minus 2. So 2 rows. Right? So now why I wrote this? I can substitute for m of n minus 1 for this term m of n minus 1. 2 times m of n minus 2 plus 1. So I can replace this m of n minus 1 with this 2 times m minus 2 plus 1. Okay? So now I can say there's a 2 outside. So I'm going to multiply the 2 inside. So it is 2 times 2 square m of n minus 2 plus 2 times 1 is 2. And then you have a 1 over here. So that 1 comes along with it. Okay? So it's basically 2 square times m of n minus 2 plus 2 plus 1. So you don't need to add it. We'll keep it as it is. Okay? So now what we'll do is apply the expression again. So for m of n minus 2 from this, I can say this is at 2 times m of n minus 3 plus 1. Just replace now n by n minus 2. So we'll have m of n minus 2 equal to 2 times m of n minus 2 minus 1, so n minus 3 plus 1. So now what I'm going to do is I'm going to replace m of n minus 2 with what? 2 times m of n minus 3 plus 1. So this is what we have. So here we have m of n minus 2. I'm going to replace that with m of n minus 2 times m of n minus 3 plus 1. So it's going to be 2 square times 2 of m of n minus 3 plus 1, right? So I'm going to replace this. So again, like we had what here? We have plus 2 plus 1. So don't forget about it. Okay? So I'm just replacing this term 2 times this m of n minus 2 by 2 times m of n minus 3 plus 1. So we have 2 square times 2 times m of n minus 3 plus 1. That's for this 2 square plus 2 plus 1. So I'm going to multiply this 2 square inside, so that will give me 2 cube times m of n minus 3, and there's a 1 here, multiplied by 2 square, you get 2 square, and then plus 2 plus 1 as it is. Alright? So you have to just watch out for the exponent of 2. That's only for this term, not for the 2 and 1. Okay? So you see a trend now. So you have m of n basically equals 2 cube times m of n minus 3 plus 2 square plus 2 plus 1. So in general, I can say m of n is like we have a 3 and then a 3 here and then lower order terms. So you have 2 cube times m of n minus 3, that's one term. Don't consider it as for everything. So this is 2 cube times m of n minus 3. Then plus 2 square plus 2 plus 1. So in general I can say this 2 to the power I times m of n minus I, so that's one term. Okay? And then the lower order term, so this is one term. And then you have the lower order terms. What are the lower order terms? Plus 2 to the power I minus 1 plus 2 to the power I minus 2 plus so on plus 2 plus 1. Okay? Because we have 3, then 2 square, 2 plus 1. So we have 2 to the power I, so 2 to the power I minus 1, I minus 2 and so on to 1. So what can we say about this? We have here 2 to the power I minus 1 plus 2 to the power I minus 2 plus so on 2 plus 1, right? So did we look at a formula to do this? Remember? There was a formula that is 1 plus 2 plus 2 square, or in general what? 1 plus a square plus so on up to a to the power n is what? A to the what? the power n plus 1 minus 1 divided by a minus 1. Okay? So what is our n here? I minus 1. So you have to substitute for n I minus 1. And what is a? A is 2. So it is 2 to the power I minus 1, which is for n, plus 1 minus 1 divided by 2 minus 1. Okay? So, of course, the denominator is 2 minus 1, that is 1, right? So you don't need to worry about that. So what about the numerator? It is I minus 1 plus 1. So that's going to be 2 to the power I minus 1. So this is 2 to the power I minus 1. What did we compute? This is for this. For all this put together, this 2 to the power I minus 1. But still this 2 to the power I m of n minus I is still there. So the whole thing is equal to 2 to the power I m of n minus I plus 2 to the power I minus 1. So what is our basic condition? The basic condition is going to be m of 1 equals 1. So what can I put for I so that I can apply this one, m of 1? So you have an m term here, right? So what is that recursion over there? You have m of n is 2 to the power I times m of n minus I plus 2 to the power I minus 1. So this is one separate term. So you want to eventually get rid of all the m's and make it just a simple expression, right? So what value I should put for I so that I can get 1 m of 1? So that I can apply the basic condition. I should be, if you put n, what happens? N minus n is 0, right? So that's not going to work. So what should be I? Just think a little bit more. And I should be, you want this to be 1, right? So n minus I has to be 1. In that case, I has to be n equals 1 plus I, if you want, you can say that, and I has to be at n minus 1. So if you cannot figure out easily, just say this has to be equal to 1, that's what we want, and you want to figure out what value of I we need to put. So if n minus I has to be 1, of course then n is 1 plus I can say I is n minus 1. So if I substitute this I to be n minus 1 over here, I'll get m of 1. Is that clear? Okay. So if you put I equals n minus 1, m of n is going to be 2 to the power n minus 1 times m of 1 plus 2 to the power n minus 1 minus 1. So what is that we have here? We have this. What is m of 1? This 1. So we can just simply say this is 2 to the power n minus 1 plus another 2 to the power n minus 1 minus 1. So if you add these two, what do you get? 2 to the power n minus 1 plus another 2 to the n minus 1, that is equal to what? 2 squares plus 2 squares is what? 2 squares plus 2 squares? Right. 2 square plus 2 square, or 2 cube plus 2 cube is? We're adding it twice. Right? So it is 2 times 2 cube. Right? So that is 2 to the power, this what was the exponent 1 plus 3, which is 2 to the power 4. Right? So likewise, you are adding 2 to the power n minus 1 twice, so it is 2 times 2 to the power n minus 1, whole thing minus this 1. Okay? This is like your 2 cube. 2 cube plus 2 cube is 2 times 2 cube, right? Twice of 2 cube. Isn't it? Any question? Here, there are two things. They are the same thing. We're adding them, twice that, right? And that's why it's 2 times 2 cubed, so it is 2 to the 1 plus 3 to the power 4, like that. So what is this? Let's simplify, one more step. So that is equal to 2 times 2 to the n minus 1 is? As the n there, don't forget n. Like what I did here, 2 times 2 cube was what? There's an exponent of 1 for 2, right?
That's 2n.
Yeah, so 1 plus 3 likewise. This is a 1 here. So 1 plus n minus 1. So what is that?
2.
The exponent. 1 plus n minus 1 is? There's a 1 here, right? N minus 1 here. So you are multiplying. So adding the exponents. So it is 2 raised to 1 plus n minus 1. What is that?
2 to the n.
Yeah, I didn't hear that so far. 2 to the n. Then you have the negative 1 there, you cannot forget that. So negative 1. So what is this in theta? Just 2 to the power n. Okay? So you should be able to do problems like this. Any question? So there are a lot more problems in the slides. Very similar problems, you have to work it out. Okay? For practice. And so for your, when is your next quiz? Your next quiz should be on 24th, right?
Yes, sir.
Yes. So let's write our thing. So this is on 24th. So today is what? Today is, we are 12. Okay. We still have time. But so for the second quiz on 24th, right? So whatever after the thing, we stop with iterative algorithms, so recursive algorithms. So we completed just now, and then what we're going to do now, and then on Tuesday. Okay. So until so recursive algorithms and 2. So this is module 1, right? And then we're going to start module 2. So until 17. So I'll tell you again on Tuesday where it ends. Okay. So then you have on the following Thursday exam 1, which will go until, so from the beginning, which is from module 1 to all the way to wherever we stop in module 2 on the 19th. Okay? There's a quiz 3 on October 1st. So I'll tell you the syllabus for that probably next week, so remind me. Okay? So it will be probably something on module 2. Okay? Module 2, we want, yeah, so let's do it like this. Whatever is probably repetitive of this, so it's easy for you to study because you already prepared for the exam. So let's go ahead and fix that. So whatever we cover only next week. For the 2 days of next week, whatever we cover will be on quiz 3. Okay? So take a picture if you want. He left. He is covering it. So, take a picture. You can send by email the picture, and I can post it to the website too. Okay. All right.
Write your email down right there. I'll send you my calendar.
My email is this. J, and then dot M E D H A N A D N J. Yes, you were. Okay, so let's move on. Did any of you have class right after this? You have a class? What class?
I have work.
Huh? What?
I said I have work.
Yeah, work. Done? Okay, so now we are going to look at module 2. I call it as classical design techniques. You might have seen some of this before, like divide and conquer and all this stuff. So we are going to look at from strategy point of view. So we are going to look at 4 strategies: brute force, decrease and conquer, example, algorithm for each strategy, at least one example, and then divide and conquer, and then transform and conquer. Okay, so as we move, we'll look at what the strategies are. Brute force is more like what? It's a common sense approach. Okay, so if you cannot come up with some really effective, optimal strategy, just try brute force. Okay, so we do that all the time. Okay, so the kind of problem we are going to do here is string matching. String matching means given a string like this, nobody noticed him, that's the string, and I want to find out whether a particular pattern. Okay, so we call the string as a text given to you, and we have a pattern, say NOT not, for example, that we want to find out whether it exists in that string or not. Okay, so what would be your strategy? This is your problem solving skill. So how would you approach this problem? If you want to find whether a given pattern appears in a string, how do you do that?
Search the whole thing.
Search the whole thing, which means you put N or P here, right? Like I put here, and compare the two. So you're comparing what? The first character here, this N with this N. If they match, you could proceed further to comparison. Compare this O with the T. They also match. And then B with the T. Is that matching? Is B and T the same? No. Which means it doesn't match here, right? So what do you need to do? Move this NOT to the next character. So you're comparing NOT now with this OBO. Right? So now what you're doing, you're comparing this O with the N. Is O and N the same?
No.
No. Now it looks like we need to compare B and O, right? But do you think we need to compare really B and O?
No.
No, because we already found out that the first characters don't match. O and N doesn't match. So we can save some comparison time by just moving to the next string, the next character, right? So we don't need to compare this B and O once we found out that O and N are not the same. So which means what I do then, I move my not to and compare this with this, BOD. So now B and N are the same? No, right? So you don't even need to compare this O and O. Even though they may be the same, like in this case, it does not help us because we want every character to match exactly the other one there. So we want the N to have an N there, O to have an O there, T to have a T here. But we don't have them here, right? So since the first character doesn't match, you can just move the next character in the original string. Right? So we can keep comparing like this until we hit a hit. Hit means everything should exactly match. So we have NOT here, it matches with the NOT here. Alright? So once we find something, we can say return true in your algorithm and say that the pattern does exist in the string. Alright? So clear? If at the worst case, what will happen, like I showed here, even though NOT is observed here, at the worst case, like if NOT was not here, something else was there, you may have to go all the way to the end. Like But notice, we are not really going all the way to the last character here and starting with NOT here. We don't need to do that because we know that after, so if you go all the way to this end, M is compared to N, but for O and T you don't even have anything to compare, right? So we need to go only up to this point where we can say HIM compared with NOT. Right? You get the idea? Okay. So what is the basic operation here if you come up with this as an algorithm? This is the algorithm we discussed, the logic. Basically, you have a string, you move it around, and we'll see a pseudocode for it soon. But what did I do each time? I moved around things. Comparison. So comparison is the basic operation. Right? Clear? So now what we want to do is evaluate how many times we will do the comparison. Okay? So the best case scenario would be what?
The first three things.
The pattern appears in the first segment like this. So if it was NOT over here, nothing or some word like here, then NOT will match with NOT here, right? So we still needed to do how many comparisons? 3 in this example, right? So we're going to put some variables here, like I showed here. N is the length of your pattern, the text, the string, okay? And M is the length of your pattern, like this NOT. So in that case, in general, the best case is you have to do M comparisons, right? Why? Because the M is the length of the pattern. So if the pattern appears right there, you will do M comparisons and you will say it is there. Is that clear? What is the worst case? Huh? You have to go all the way to this end, right? So that's why I have some numbers here to find out easily what is the length that you have to move. You see that if you the index, you always start from 0, right? So for the text you have 0, 1, 2, 3, 4 up to 17. So you have 0 to 17, that's why the given text is of length 18 characters, n is 18. Okay? And our M, the pattern is of 3 characters long, and its index is 0, 1, 2. Right? So, you see here, this n, you compare with h, which is at index 15. Right? So we have n is 18 there, m is 3, so m is 3 characters long. So the last comparison starts at 15. Right? The 15 can it be written as like this? N minus m, that's what it is. Right? So if you move around from 0, so this is, we are comparing at the 0th position, and then you are comparing at index 1. Then as you move this knot, the next time you are at index 2 and so on, as like that you move until index 15. Right? So you move this knot like this. So what I want to do is count this. How many? This is 0, 1, so this is 2, then like 2 different things, right? 2, what do you call, this 2, this is one, sorry, this is one block. Let's get block, okay? So this is one block. How many blocks we need to do? This is another block, right? This OBO. Then the third block is BOD. Then the fourth block is ODY. Then the fifth block is what? DY this, right? We keep moving. This is the first block. What is the first block? NOB. We compare NOB with NOT. That's the first block. Then move by one character. Then move again by one character. In each block, how many comparisons you are doing? 3 at the worst case again, right? So if you don't get a match, you can stop comparing the rest of the characters within a block. Isn't it? Is that clear? So in each block you will do how many comparisons? At the worst case? 3. We will do in this example 3. So in general, M comparisons. comparisons. The m is the length of your pattern. And how many such blocks we have? That's what the 15 counts. How many such blocks we have? Actually, 16 blocks in this case, because start from 0. So this is our first block starting from 0, and then from 1 to 3 is our second block, then 2 to 4 is our third block, then 3, 4, 5 is our fourth block, and so on. Then 15, 16, 17 is the last block. Right? So we have actually 16 blocks. It's like counting from 0, lower limit I equals 0 to 15, 1. Remember that? Right? How many blocks we have? From the index 0 to index 15 in this example. Right? So that's equal to 15 minus 0 plus 1. Upper limit minus lower limit plus 1. Okay? So that is 16. So likewise, if you have in general, this is I equal to 0 to what? This 15 is nothing but, if you have n and m, it is n minus m. Right? So this index is actually n minus m. So the last index where you start comparing is n minus m. 1. So that's equal to n minus m minus the 0 plus 1. So this is n minus m plus 1 blocks. So you have these many blocks that you have to compare. Okay? Because you're starting from index 0, remember that. So we have n minus m plus 1 blocks to compare, and in each block you will have to do, at the worst case, m comparisons. Right? And we're looking at worst case complexity. Right? So put together these two things. This many blocks, these many comparisons per block, so the worst case number of comparisons totally is what? These many blocks and these many comparisons per block at the worst case. So m times n minus m plus 1, that's all it is. Product of the two. Alright? So we're not going to simplify this further, but like not going to multiply inside, but I'm going to say this is some theta of m, because m is a variable, the length of your pattern. And typically, like we see here, your string is going to be so long, like this, of length n characters, and your pattern is going to be a smaller one. Right? So I can say n minus m plus 1 as what? Theta of, which is more dominating term within this term, within this square bracket. N minus m plus 1, or which one? And in the m minus n plus 1, which term is more dominant? N, right? Because the length of the string is typically much larger than the pattern that you want to search for. So I can say this is theta of nm. Is it clear? Okay. So we're doing m comparisons per block, and how many comparisons? N minus m plus 1 blocks. Alright? Remember that n minus m plus 1 will do some sample problems also. So let's look at the pseudo code for this. Whatever we discussed is actually a pseudo code. So you're going from I equals 0 to n minus m, that's the outer loop, to move the blocks. And then j equals 0 for your pattern to start with the first character. And forget about this for the time being. You're doing what? Comparison. What you're doing comparison, let's do that small string here. We have nobody and we have not.